Hi. So, who knows IPTFS? You do a little, and you don't, and you don't. Okay, so let's see. So I'm going to go through the protocol first, and then I'll go cover the overview of the implementation. The reason we use TFS is to protect against traffic analysis, and that's basically you might encrypt your traffic, but it can still be, you can still derive information from it based on things like packet size or frequency of when the packet was sent. For example, there was a presentation at Usenix a while ago, some years ago, where they actually discovered what movie was playing, even though it was in an IPsec tunnel. They were able to say it was Die Hard because they could analyze the packet traffic. So that's what TFS is looking at doing. And you hide this with sometimes called TFC, traffic flow confidentiality. You'll see it referred to that in the IPsec RFC. So the current available option is ESP plus padding. This has real suboptimal performance, obviously, if you have a 64-byte packet and you're sending 1,500 byte packets for every 64-byte packet. So what IPTFS tries to do, or what it does do, is fragments and aggregates inner traffic into outer packets, so that this minimizes latency and increases bandwidth. So this is an example of the bandwidth efficiency. The red here is the required overhead. This is for ESP plus. This is for ESP plus. You can see that, or this is ESP plus padding, so you see all the overhead, an average with it. This is IPTFS. It's excellent data to overhead. And it's even better than Ethernet. Because Ethernet, you have, for every packet, you have Ethernet overhead. So this is another graph that sort of shows, given different packet sizes, which are not legible. Not legible there, but you can look it up later. So the key design points was to use standards to be better than ESP with padding. Happy birthday. That's right, so we use ESP. So this is an example packet flow. You'll see this is the outer traffic. So each packet is the same size, 1404, each payload. Payload is 1404 here. Down here is the actual inner traffic, or the user load. So you see 750, 750. So we have 1 3/4 of a packet encapsulated in the first ESP payload. Here we have 2. We have the end of this one plus 2 more, plus the beginning of a third. And then this is an example of a packet. So the way we achieve the TFS is by using fixed size packets and sending at a constant rate. So no matter what traffic is inside, all you see on the outside is the same exact size packet at exactly the same interval. In the standard, we say that variations are allowed. So even though that this is what we're going for, we don't mandate it. So the receiver just always accepts the traffic. That allows for, many different uses. So we have this is basically implementing what could be called a fire hose, right? You turned on a 10 gig packet rate, right? 10 gig, be sending 10 gig all the time. So it was important to have a congestion control so that if you're doing that over the internet, you back off instead of just shutting down all the TCP around you. Yeah. So we had to do TCP friendly congestion control to get it through the IETF. And that's what basically drove how we did the packet, and what data we included in the congestion control header was all the data required to satisfy these RFCs. So we also have a non-congestion control mode, and this is when you own the domain, and you know you want 10 gig and you don't want it backed off because it's the most important traffic that you have or whatever, and it's all within your network, then we don't want it to use congestion control in that case, or you might not want it to. So we use IKV2 to signal EFS, and it happens during the auth and child SA. And it's the same as like tunnel mode is negotiated or whatever. It sends not tunnel. Anyway, you send the notification, and either it works or it doesn't. The other side accepts it or it doesn't. So this is the packet format. Yesterday, Anthony mentioned the subtype. He's using 3, right? So we 0 is non-congestion control and 1 is congestion control. The rest of the 255 are free. Oh, I don't know. I don't think it's used. No, yeah, probably. I don't know why AIM says it's used. They usually have a RC next to it. It says reserved or whatever. Okay, so anyway, this header is common, and then sometimes we have a bigger header for congestion control, and then below that is the data blocks, which are how the packets are included. This is the non-congestion control header. It's 32 bits. The data blocks, we're using we use the first nibble to identify who else does that. IP does that, right? So IP packets, first nibble is a 4. In IPv6, the first nibble is a 6. So we basically don't have any type specific framing that we're adding, right? We just jam the packets in, and the beginning of the packet identifies itself as IPv4, v6, or if it's a 0, it's a pad. And padding always occurs at the end. So there's only ever one pad data block. And it fills out the rest of the packet. This is the IKE notification. Here's the congestion control header, as mentioned yesterday, and this is basically all the information we need to do the congestion control, like tval and techo we set our own timestamp in tval, and the other side sends back our tval in techo, and that's how we determine round trip time. We also add in echo delay and transmit delay. Figure out round trip time. That's not right. Yeah, okay. Oh, right. That's so you can subtract that delay. But like echo delay is that's the amount of time the receiver is saying this packet spent this much time in my queue. Right? Because if you're actually trying to get an accurate measurement of round trip time, if your round trip time is 100 microseconds, but it sat in the queue for 1 millisecond, right? If you don't have that, if you're not subtracting out the echo delay, it looks like your round trip time is a lot longer than it really is. But I think you're supposed to include that in the TCP friendly anyway. So that's the overview of the protocol. Now, the work we've done so far is not constant send rate. It's what we're about to merge into the kernel is demand driven. So it's really just using the fragmentation and aggregation, and it just sends those out as needed. So if you're sending really slowly one packet, only one packet will be encapsulated. But if you send, line rate 64-bit packets, a bunch of 64-bit packets into a single TFS frame. So, but next we want to do the constant send rate to get the security. And the main thing, this is kind of a busy slide, and it's my design from VPP, which was our original implementation. But the main reason I put it here was to show the isolation. Very critical that the packets that you send are not affected by the user load, right? Because that's the information that you'd be connotating, right? Even if your packet size is not, even if your packet size is the same every time, you vary when you send the packet based on load that you receive from the user. You've now leaked information, leaked it from the user, from the red side to the black side. So we absolutely cannot have the user load affect the timing of the sent packets. So they have to be isolated. So the key right here is these things. These are two lockless rings. This generates our packets with data, user data in it. This is a different core that this can be shared amongst all the SAs, but this basically generates 0 packets, so packets that are just all pad. So if I don't have any traffic, I need to still send something. So that's what this generates. Over here, this machine generates packets that are padded. So the output of either one of these machines is a 15, say it's 1500 bytes is the outer size. These are both generating 1500 byte packets. So this is the isolation core. This is the send core. So this guy basically is pulling up one finished packet from one of these lockless rings, and it's going to look at both rings. It has to look at both, because if you look at only one and you don't look at the other one, you're going to leak information, because if you go to the second one, the timing will be different. This does nothing else but send packets. Can do other things as long as that's not information that as long as it has nothing to do with the offered load, right? The red traffic. But technically, if you're because you're on a multitasking system in Linux, right? Right, but well, you isolate this, right? And you basically, like in BPP, that it was really critical to isolate the core, right? So we ISO CP, the ISO, yeah. So we pull it out of rotation, but even beyond that, we had to go in and it still gets used by the kernel, right? There's like some interrupts that it still services. Right, you have to do all of this, right? And so once you do that, and then it's really isolated. Now, technically, what I was saying though is that Linux could run other processes here, right? You could run other processes on this core. They just have to be completely unrelated to the user traffic. I don't know if that's doable. I think in general, you're just going to want to burn a core. Right. Just yeah, just if you can pin it like a K-thread, right? Yeah, I think so. That's what I'm thinking. So that's why I put this up here, right? Now, these don't have to be, these technically don't have to run on their own core, right? Because they're just filling these. The only thing that has to happen is that you always have to have at least one add packet, right? Because I need to be able to send a packet when I need to send a packet. So generally speaking, this runs much faster than it needs to, right? Like it's just generating zeroed out packets. Unless you're trying to push the machine like, oh, I'm going to go 40 gig, right? Like now you're at the point you can barely even do it with zeros. Other than that, you're going to have enough. So that's the general idea. On the receive side, there's no, I don't even know why I included this, since it's no relevance. Process the packets as you receive them. And so the last thing that I wanted to show was, I don't know, it's always fun to actually see some analysis, right, of like code. So what we're going to look at here, I got some cool graphs. And the way I did the analysis was we did a mirrored switch port. So that we have the traffic going through a switch, and then we mirror the traffic to another port. And on that port, we have a Mellanox card plugged in, and then we use hardware timestamps as we receive packets that we're sniffing from the switch. And so what we're going to do is we want really high resolution packet timestamps of when each packet went out, and also when we sent the packets. So what you're going to see is the top. Show you. This is one where you can see the effect. So this is the user load down here. This is the TFS traffic, and what you see up there is the delta between packets, right? So the amount of, if the bar is wider, that means there was a bigger difference between the away from the perfect interval. So the closer you get to a line, the closer you are to actually being perfect. And you can see, I mean, the time is shifted here. Correlation, right? We have user load here. We have the effect of it on the traffic here. This was for, you can't read it, but this is for chaining. And everyone that you actually see in effect was the code that I use chaining with, where I chained buffers versus copy, where I copied the data out of the packet. This is where I copied. Goes away. And some of the later ones, I'm not entirely sure that it completely went away, but it's pretty close. You'll see here. So this is an impulse, right? So we're doing 4 impulses. And these are, read, I'm so sorry. The bottom is a 64-byte packet, 4 impulse. And you can see there's 4 little humps there you can kind of see. Much less visible. I'm not sure it's gone here, but it's much less visible in the copy. And then this is 1,500-byte packets. The user load is 1,500 bytes instead of 64. Another 4 impulses. This one is the one I think I can kind of see it still. So we didn't get perfect. And then I just included this one. It's more impulses, but it's too hard to read the data. I mean, this is just showing we did do multiple different types of tests. That's it for the protocol. Has any questions? Absolutely, right. You send it, but blanks, throw them away. Yeah. But people, there's different reasons people like this. I paid for it is one of them. Not kidding, right? Like to satisfy an SLA. If I'm paying AT&T so much money for a 10 gig link, I'm going to send 10 gig on it, and you're going to give it to me, and I'm going to notice when I don't get it, right? The other times where you might have really intermittent traffic, but you don't care, is like a missile site. Right? You don't want to see when the activity starts at the missile site. Kind of a big giveaway about the launch. Yeah, so mainly those are like where you really do want to hide it, and some people actually guarantee that they're not just to guarantee they're getting their money's worth, right, but to guarantee that it's up and available, that you're always getting that. So whenever you do want to send, you're getting immediately be getting the full bandwidth, not burning new holes or starting new paths or ECMPs or anything like that. So the other presentation I have is the sorter, and it's the implementation. So quick history. We've done 7 patches. We did 2 requests for comments, and then basically I got a lot of nice reviews, Anthony and some other folks. Of course, I sat and worked with Stefan. You don't get any credit here because he didn't comment on patches. We just sat down and like worked through the code. So there was a lot of changes that happened with Stefan. And then, yeah, this just documents what we, let me hit, how do I do that? Yeah, you could call it that. Yeah. Yeah. Yep. Posyochronous, but hopefully synchronous, right? As close to synchronous as we can get. Yeah. In slide byte or sonnet slide byte, swap byte. So, yeah, this is just documenting. I missed a few things Anthony caught that I missed clone for cloning essays, so we added that in. And then Anthony did the work to add essay directions to directionality to essays in, inbound or outbound. And so we added that functionality in. And then this last one I posted, I've got some feedback. Basically, it's just warnings, compile warnings. So we're pretty close. I mean, if anybody else wants to review this, don't delay. It'll be going in soon, hopefully. This is the IP route 2 changes. You see there's 4, 1, 2, 3, 4, 5, 6 values. 2 of them are input values, drop time. So we have to hold packets in case we have reordering. We have to put things back in order because packets are in order to put the fragments back together. You don't necessarily always need that. Like we could have done framing where we sequence numbered every single fragment, or like that's what IP does, right? IP has identifiers with the fragments, so you can put them back together. But since we're streaming, it's not like IP, right? We know generally we're sending this constant rate flow. It makes putting it back together really simple. So we didn't want to burn a lot of bits and complexity. But we do require putting them back in order. So that's what the input ones are. The reorder window size, how many you're willing to be out of order with. So if you make your reorder window 10, that means the 10 packets can be out of order. After that, it would be dropping. And then drop time is how long to wait for the next packet. Don't fragment means what it sounds like. Don't fragment and only aggregate. Initial delay is how long to, so we have this feature where we will delay if our queue is empty and we have nothing to send. First packet that comes in, the init delay is the amount of time to wait to see if we get a second packet, see if we can aggregate. Max queue size is for the other side of things when we have too much traffic coming, and so we're queuing it up. How much are we willing to queue up before we start dropping? And then packet size can be 0, in which case path MCU will be used to size the packet. Otherwise, you can set the size of the outer packet, the CFS packet, right? So you could say 1,000. For really simple, trying to deal with really simple MCU issues, you could just set it at like 1280 or whatever, the guaranteed size. And then, 1,500 byte packets will fit just fine, but they're going to be fragmented inside those carrying outer packets. But you'll always go through.
Does it make like a copy the packet?
Yeah. So it doesn't copy it, but it moves the SKB into the queue. Pointer. It's the amount of bytes in the queue. data payload. So if you have a 1500 byte packet in your SKB gets queued as long as there's 1500 left in the queue. Yeah. You're not copying, no. But I hold on to the SKB, right? Get it in, take it, and I queue it up. But I'm just putting it on a list, right? I'm not actually copying. Right, because yeah, if you said it's like 100, yeah, right. Yeah, nothing's that small. Not even the IP header, right? Yes. There's a mid counter. I think I used the mid counter there, yeah. Maybe I didn't, but I think I did. Yeah. Yeah, I think I did. You could double check. Right. Yeah, we called this max queue size we changed the name. Oh no, the name that I'm going to tell you you'll like less. Because it doesn't make as much sense for demand, right? But we called max latency. So when we're only working with the constant rate, we call it the max latency. So well, it's documented as being maximum number of bytes allowed. What? Oh yeah. I don't know. But but no. But I give this, right. Where is it there? Right. So you can sysctl change even the default, right? So if you don't like the default max queue size being a megabyte, you can change it here so that all your new SAs that are unspecified use. Right. So this is the man page of IP route has all the definition of what those values are. Yeah. For init delay. Just for response time in the kernel. I mean, if you care that if you're going down to nanoseconds, like why bother? Just it's really kind of a like a goofy optimization, right? I mean, generally speaking, you're going to get user load that's bursting in, right, and coming in line rate. You're aggregating. This is just like a little extra. It's easy enough to do, right? But yeah, we're not going to I wasn't going to over engineer it, right? Because it's really just about like trying to aggregate another packet in. Yeah, that's why. So the implementation is in one file. I mean, we touched other files, which I'll cover, but the IPTFS implementation is in that file. And then, the global functions and the static functions prefixes. And it's 3 sections, a state and then ingress and egress. This was confusing to somebody on the list, one of the reviewers. So sort of be confusing that the output functions are tunnel ingress, right? And tunnel egress are the input functions. When I receive traffic, input traffic, actually traffic in the tunnel, but to leave the tunnel. So what did we change in the SA state? We added a callback structure and a data structure. Data, for the TFS state and the callbacks. basically these are the callbacks, and they get put throughout from code to do the different things, right? So that's just a big thing. I talk about them here, right? So create state and delete state get called when your essay is being created or deleted. User init and copy to user are the receiving netlink and copying netlink back out to describe an essay. Clone is for cloning an essay. Essay length is used for that too. Or no, essay length is yeah, that's what that's. Get inner MTU is basically used to determine what the inner MTU is. And then these functions are called doing the output to, basically implement a mode, right? That's what all these do. Mm-hmm. Right. So the reason we're doing this is so we can compile a mode as a module. When I originally had written this, it wasn't capable of doing that, right? I just put in the TFS calls directly into the XForm code. So we abstracted it out into the callbacks so that you could load TFS as a module. I don't think this is it. So we added these 4 sysctls to basically set the defaults. And there's the running code. So I don't expect everyone to write this down. We can make the slides available. But I have a development environment, the top one, and you can download that and should be able to type make to build. It'll build a kernel and a build root. Last time I did a presentation of my testing framework too, but that's available in MuNet. And if you do the development environment, oops, no, not the demo. You can type make test. You'll have to actually download MuNet and stuff. So I don't know, Anthony's done it, but it required some hand holding. It didn't work out of the box. Yeah, Buildroot is very, like, I don't touch that thing, man. Like, I had to because, oh, you mean you're just up to, yeah, I don't touch it. Yeah, no, that's too much work. Yeah. So I have to update it the only time I update it is when something in the kernel requires it, right? Like there'll be a kernel change that the current build root, it's tagged. If you look in the make file, I grab a specific. Oh no. Yeah, that thing breaks like, oh, yeah, I think that might have been one of those slides I skipped over. That is interesting. So the reason it's faster is because of cache lines. So, for example, when you go to like an SKB, right? Like just touching an SKB, you're going to load 64 bytes, right? So, and then touching the top of the header of the first packet, it doesn't matter if you just touch 1 byte, right? You're going to get 64 bytes. So you're going to get the entire IP header. But if you're working in a 40 byte packet or whatever, you're going to get the whole packet in one cache line. So it just ends up, and it actually is bigger. I don't know what the cutover is. It's around 256. Because what happens when you're doing chaining, right, is that you're touching all these SKBs and you're loading cache lines to chain, right? And it ends up being just as fast to just copy the headers, all these small bytes. And it ends up being like the 256 byte packets. It starts getting cheaper to chain than it is to copy. I don't know where that was. That is in. Yeah. No, I guess it wasn't. Yeah. Oh, maybe it was in the other presentation. Last time I did this demo, but I didn't plan to do it this time. So, right. So the basic takeaway is that hopefully we'll get the demand stuff in real soon now. Then I'll be working on probably more than was supposed to be done this year, but I don't know if I'll get done with the constant rate sign by this year. Probably in next year. Perfect. I think that's it, right? Unless anybody has anything else to talk about. Yeah. 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 That's why I put the subtype there, so you could just, it was, the idea was we burned a protocol number, so,
Yeah.
Why not just let other people use the protocol number too? Use it too, if you wanted to.
I don't know, we will end up getting the protocol number, but if as it's proposed now, we're trying to use the subtype, whatever next available subtype is. So there are two questions. Like one is, can we use it without IPTFS on a kernel without IPTFS being negotiated?
I think so, as long as you pick it, as long as you get IANA signed. I think we required that, right?
Without I negotiation.
Yeah, you don't need to do any of that, but you at least need to reserve your packet format.
Yeah.
And say type 3 is for ESP ping.
And the bandwidth information, is that coming from the history of the packets, or is it like, can I query the bandwidth and say, tell me how do I get the available bandwidth right now?
So, yeah, you mentioned available bandwidth. I don't know that I calculate available bandwidth unless you mean the congestion control algorithm.
That's what I meant.
Yeah, I haven't even written the code yet.
Yeah.
So, I can't tell you how to do that.
Okay.
But it's interesting, maybe keeping in mind that it'd be useful to keep that as a queryable value.
Yeah, because it's one of the things is like the ping. What we're trying to do is like to see like if our backup path has enough bandwidth available, then we switch over to that's the use case typically. Like
right,
like you have two paths and one primary path and the backup path.
Yeah.
And if there's still bandwidth available, you can burn it and use it. So keep that in mind, like that the use case.
Right. No, I said I wasn't going to demo, but it doesn't take me, since we have a little time, I might as well run. I think I already have one running. I'll start it over. So I'm in that development environment, right? Oh, that's not what's showing, is it? I think I just need to quit. My Windows system now is going to not work very well because it's too big, but so this is the development environment I mentioned. The main interesting thing here is that I have the test directory. So there's various different tests that I'm going to run SimpleNet, which we can take a look at that. So this uses MuNet, which has this YAML format. MuNet basically creates topologies where each node can be Linux namespace. It could be in this case, it'll be a KMU running a Linux, our Linux kernel we built on our build root. It also can be containers. So you can use Docker containers. But like I said, in this case, our host is H1 and R1. Host is a Linux namespace. And R1, even though it's called Linux, is actually the KMU running IPTFS kernels. So, and then the connections, I define the networks up here. These are basically all VFs with bridges. So we have a management network, a net 0, net 1, and net 2. Do I have a diagram up there? No. Oh, I know where. So the diagram. Anyway, this is a description of and you can see I show the IP packet, the IP prefixes for each network. UNet automatically like numbers everything and configures it for you when you run the simulation. So this is what you do to define it, and then the test file is Python using PyTest. But this I think has my picture. Right. So this is going to create host on each side. That should be H2. I don't know why one mistake. And then router 1 to router 2. So net 1 is the black link, and the red links are on each side. So that's what I'm going to run. And I'm actually going to run the test, which just does some pings. You can see it's setting up the IPsec state and policy here. And then the test itself, you can see here it's doing pings. So we'll run that test. And I add the flags. Oh, it's down here. You got pause at end and PCAP. This says capture packets on net 0 and net 1. So it's going to use tmux to create a bunch of windows to show all that stuff. Hopefully, since I shrunk the font or made the font big, it's going to be pretty busy. But you can see down here, these are the two network. So this is red traffic, right? You can see the ICMP. And then up there, ESP. And you can see we're not doing fixed size packets, right? They're 158 bytes. So it's just on demand. It's using the framing. If we sent it fast enough, you would actually see it turn into aggregate packets. They'd be a little bit bigger. And then we can, so part of the, like I said, it's pause at end, so you can go into a CLI mode. I'm sitting at this CLI, and I could SSH in over the management network. If you set a management network, you can do a console, which is using the serial port. So this is the serial port on router 1. Since we set a management port up, as long as your networking isn't locked up, because if we're also testing networking code, so we can. That's why you want console. But since we have a management network, you can see here the IP route showing the essays in router 1, and then you can see IPTFS options. Yeah. Well, do you see? I didn't. Your changes here, right? So there's. This is important to Anthony, so I want to point it out. If we look at the top direction in, it's only reporting inbound attributes, and down here you can see it's direction out. We're only talking about the outbound attributes here. So the other thing we're talking about is there's a test in here, Anthony, that's the MTU test. Where is that? So I played around with this a little bit because you were trying to do bigger packets they're really hard to get to make Linux work. It's just, frankly, TFS can't fix this problem. It's what does work is 1500 byte packets, right? So if you're sending 1500 byte packets, you can have smaller tunnels and things will work, right? TFS will do its job right. But when you start trying to send 2K and 9K packets, you have to tweak a lot of stuff for it to get through the stack. And it's not just TFS. It's like you got to go in and set any route that it touches has to also have an MTU specified as like 9K, because if it hit, like, it'll hit the route. The route defaults to 1500 MTU. It drops the packet. It's shocking how many different places it's trying to drop packets that are oversized. You wish it was just on the tunnel interface, right? So I do have this MTU test. I just wanted to point out, but in this case, I'm setting the, well, I do set it to 9K, but I do this one at 1400, so I'm shrinking it down. And then the actual test, I think I shrink them even smaller. Right. Actually, if you look here, set up ton route, right? I'm setting the MTU on the ton route to 65K. Maybe this test does actually, yeah, so this is, so if you look at this test, I guess it does, I mean, this test passes, so. But all the work you have to do is encapsulated here.
The only difference is on my essay, I was setting don't defrag as a,
Don't frag, yeah.
don't frag as a,
You were turning it on.
yeah, I was turning default. That was, but I ended up there accidentally, but then I noticed a lot of bugs.
Yeah, so that definitely won't work, right? Like, because if it can't fragment, it can't send bigger than the outer packet. Needs to fragment. So anyway, that's the simulation environment. It's pretty cool. If you're really interested in that environment, go to the last Netdev. There was a thing on the last day called "My Foo's Better Than Your Foo," and it was basically like, come show off your development environment. And so I presented remotely. Got pretty good. He gave me a fire icon, so I guess that was pretty cool. But anyway, yeah, I cover like all the different features that I use here, including like GDB, the kernel, which all of it's available with like flags. You can say GDB router 1, and then you can actually specify a function inside the kernel that you want to break at. And then when you run the simulation, it actually will load the kernel into, using KMove, load the kernel into GDB and set a breakpoint and stop when you hit that breakpoint. So it's pretty powerful, and it's pretty useful for debugging kernel. Yeah, to the slides. No, I don't have a link yet, but yeah, well, I guess send it to the IP Workshop. Are you on the workshop mailing list? Yeah. Yeah, so, but the link to that environment is in the slides. So as long as we do the slides, that was that slide I showed at the end.